Okay, so we've checked how the train and test errors depend on the complexity of our polynomial model. And this is a two example. So here we can simply control the complexity of our model by adding or dropping some features, polynomial features. And in any or almost any real problem, we cannot control the complexity of the whole pipeline in this way. Imagine that you have some experimental data, you have a lot of features, say 100 features, 200, and you cannot just drop some of them just because you want to decrease the complexity of your model. And in this case, you need some ways to control the complexity of a linear model itself, not the whole pipeline, including some feature selection steps or feature generation steps, as we did before. And the question is, how can we at least measure the complexity of a linear model? So first we want to measure it somehow, and then we want to control it. Let's start with a simple exercise. So now we have two models. Just to remind you that the first one was fitted with the training sample of 10 points, and the second one had the training sample consisting of 50 points. And they looks like this curve. So again, I regenerated the data set one more time, so it's a new curve again. But as we can see, we have huge oscillations here, and it's still the same degree 8 of polynomial. And this function, again, this is now trained with 50 points. It's exactly the same model. 8 polynomials and a linear model just after the polynomial transformer. So let's try to analyze these two models. So this one is model to complex, and as we can see, it's a pipeline which consists of two steps. The first one is polynomial features, and the second one linear regression. Just to remind you that linear regression model is a very simple linear combination of features, and the parameters of this model, the parameters we wanted to feed during the optimization of the objective function, is just a set of coefficients within this linear combination. And let's try to extract these coefficients from the model and then compare coefficients for this model to complex with the coefficients for the just right model. Okay, we need some Python indexing. So pipeline models contains steps within this property. So you see that now it's again features, and it's a list with two elements. We need the second one. So now it's linear regression, and again here we have just the name. It's a string variable, and the instance of our linear model. So again, we use indexing to extract this linear regression instance, and within we need a special property called coef. It's just a set of coefficients. So we can extract it in this way. I just wanted to show you that model to complex, again degree equal to 8, and model just right, again the same, degree equal to 8. And here we extracted coefficients for this model and for this model. And we can compare these coefficients. So actually a little bit shifted, but it's the same number of coefficients. So this one is for the constant term equal to 0. And actually, you may remember that we do not have this constant term within our model, original model. And then we have a set of coefficients for the remaining polynomial features. So x in the power of 2, x in the power of 3, etc., x in the power of 8. And we can notice that the values of these coefficients, absolute values, especially for the polynomials with high degrees, say this is 4, this is 6, and we have much higher values for this two complex model than for the just right model. We can try actually, where is it? We can try to, yeah, here it is. No, this is just right. Model 2 complex, okay. I just want to create this model is a bad one, I agree, but it's not terrible, right? We do not have these huge oscillations. So I just want to create a new training sample. What is the code for this? Yeah. And to select a really terrible case, yeah, for example, this one. So we see that we have some bumps here and there, really large negative R square. So let's try to analyze this model instead of the original model 2 complex. So I need to print these coefficients again. And you can see that now the model is definitely even much more complex than the previous one. And as we can see, the coefficients, the absolute values of coefficients are also much higher than it was before, and much higher than coefficients for exactly the same parametric model. I mean, it's just the same combination of polynomials, but with just different coefficients. So from this example, we can also imagine that we have, say, degree equal to 4. We know that this is the optimal value for this particular problem. And this model can also be represented, I mean, degree polynomial with degree equal to 4 is also can be represented as polynomial with degree equal to 8. We just need to remove the last 4 coefficients, set it to 0, right? And then our model with 8 polynomials will become the model with degree equal to 4. And again, in other words, for the optimal model, these values from 5 to 8 will be equal to 0. So again, these values will be smaller than we have for these two complex model. So it's kind of an intuition why do we need small coefficients and why the absolute values of these coefficients can be used as a measure of model complexity. So this is kind of a practical justification that the absolute values of these coefficients are a useful measure of model complexity. There are some statistical justification behind. For example, we can calculate the mean and the variance for our coefficients, and it can be shown that for bad models we have really large variance, for example. But it's out of scope of our today's lecture, so we just want to answer a more practical question. Can we control the complexity? Can we limit the absolute values of our coefficients to move this transition from too complex model to just right model, even if we have only 10 points? So imagine that we do not have 50 points, but we still want to train the same model with 8 degree equal to 8. So how can we constrain, how can we limit the coefficients within this linear combination? And actually we can do it. We can just modify our objective function, and it can be done in two ways. So the most direct way is that we can want to solve a constraint optimization problem. We want to minimize the sum of squares with some additional constraint. So now we want to introduce some limitations for the norm of our set of coefficients. And actually these two forms are just identical, and for some values of lambda and lambda hat. And this is a constraint optimization problem, and this one is just the same problem written in a different way. So here we measure the absolute values of coefficients using L square norm, squared L2 norm, or we can use a different way to penalize the model. Again, here it's just one formulation, similar to the first equation, but again here we can use exactly the same way to transform this optimization problem into a constraint one. So here we use, instead of L2 norm, we use L1 norm of our coefficients. So it seems that this just slightly different ways to solve exactly the same problem, to control the absolute values of our coefficients somehow. Actually, there is a difference, but in both cases we do limit these coefficients as we wanted. So there is a geometrical illustration of this constraint problem. So imagine that we have just two coefficients. We have a linear model with just two coefficients, so we work with two-dimensional data, or with two polynomials equal degree 1 and 2. And then we want to visualize the space of our coefficients. So it's beta, it's the same coefficients as we have in our linear combination. And this is the optimal point. This is the point with the smallest mean squared error. So this is the solution of the unconstrained problem. And then we want to add some constraints. It means that we want to find a point somewhere within our this blue region which satisfy the constraint. So here L2 squared L2 norm is say 1 or less, and here L1 norm 1 or less. And we want to find the point with the smallest value of mean squared error. And just to remind you that mean squared error is obviously a quadratic function, and here we can plot levels of this function and find the optimal point, and here, just believe me, then we will just play with both ways to introduce penalties. The core difference is that if we have L2 norm, then the optimal point will be somewhere between the origin and the optimal point. But if we work with L1 penalty and L1 norm, then for some sizes of this region, for small regions, the optimal point will be somewhere on the coordinate axis. So here you see that the optimal point is here, and it means that beta 1 is just equal to 0. And it means that we effectively remove one feature from our linear combination. And this is the core difference. Both penalties allows us to control the complexity of our model, but L1 also allows us to remove some features from the final model. This is the core difference. Okay. So now we know how can we constrain the coefficients, and the hypothesis is that we can control the complexity of our model modifying the parameter lambda here, this parameter. Actually, in scikit-learn it's called lambda. Oh, sorry, alpha, I'm sorry. Let's try to work with this concept. So this is a simple example. So here we have one training sample for both models. So the first one is just exactly the same model as we had before, polynomial features with degree 8. I don't know why it's 15 here. We can use just 10. Okay. Again, 10 points again, and as you can see, it's exactly the same set of features for both models, but in one case I use the default linear regression model, and you see it's too complex, obviously, with large negative R2. And here it seems that this ridge model is even too simple, right? It seems that we can make it more complex. Let's try. As I said, we can control the complexity of our model, of our ridge model, using this parameter alpha. It's just directly related to the optimization problem I showed above. So alpha, for large values of alpha, the contribution of penalty is high, right? And for small values of alpha, the contribution is small, and for alpha equal to 0, the contribution is equal to 0. So for alpha equal to 0, the output model is just a simple linear model, linear regression without any additional constraints. So we need a value somewhere between 0 and 1, right? 1 is too high, 0 is too low. So we can try to find a good value, say 0.1. Let's try 0.1. Yeah, it seems that now we have a really nice model which is smooth, which allows us to describe the function reasonably well, especially if we compare this model with this one. But again, the set of features, the set of polynomials is exactly the same in both cases. So we just modified the way how we estimate the coefficients of our model. Okay, so now we can try to reproduce these curves for different values of model complexity. So now we know that we do control the complexity modifying the parameter, the regularization parameter alpha. Usually, it's the most convenient way to modify it is to use log scale. So here I created a set of values, alpha values, from -6 to 3, and then feed two models, so rich and Lhasa model, with different values of alpha, so 10 in the power of -6, 10 in the power of -half and -5.5, etc., till 10 in the power of 3. And the same for Lhasa. And also we calculate train and test errors for both rich and Lhasa models, and then just plot it. So just a simple way to compare different models. And as we can see, it looks actually all the curves look like the curves we created for different degrees. So for two large values of alpha, so here we have two simple models. Actually, here we have just a constant fit. So for large alpha, 10 in the power of 3, the contribution from MSE is can be actually ignored, because any nonlinear model, actually any model with a non-zero coefficient, contributes to the overall objective functions more than we can get from MSE term. So here we have a constant fit. So you see that both for Ridge and Lhasa, the errors are just the same on the train set and on the test set. Then if we decrease the parameter alpha and consequently increase the complexity of our model, then both train and test errors become to go to optimal values, right? And these optimal values are different for Lasso and for each, but the overall profile for these dashed curves it's Lasso, and for these solid curves it's for each. The overall profile is almost identical, right? For Lasso we just shift it to the left, say by 2 to maybe 1.5 degrees. And I just want to remind you that when we used just linear model, the error was somewhere here. So the error was too high. At this end of the plot, we can say that here it's just an unconstrained model. So here it's just equal to just a linear model, simple linear regression. We can use our our test sample to identify the right complexity. Okay, so the last part of this exercise is to compare coefficients for Ridge and Lasso models. As I tried to explain above, the L1 penalty, the core difference between L1 and L2 is that L1 penalty allows us to remove some terms from this linear combination, or in other words, to make some coefficients equal to 0. I mean identical to 0, not close to 0, like 10 in the power of minus 5, but just identical to 0. Let's compare two optimal models. So here I just pre-select some values, but it's close to optimal values from the graph above. And I want to compare three models. The first one is just ordinary linear regression. The second one is ridge with more or less optimal alpha. And the third one is lasso, again with more or less optimal parameters. And in this case, I just create these models and created these models and fitted them, and then extract coefficients exactly in the same way. Again, we have pipelines with several steps. We need the second step, and within the second step, the first item is the name of the procedure, and the second item is the model itself. And then from this model, I want to extract coefficients. So these are coefficients for the linear model. So as we can see again, the absolute values of these coefficients, especially for the highest degrees, these values are really high. So now we can compare it with ridge coefficients, and as we can see, it's the absolute values, all absolute values or almost all absolute values are less than 1. So there is a huge difference in terms of L2 norm of this vector, these two vectors. And now we can compare these coefficients with lasso. And as we can see, again, the absolute values of coefficients are similar for ridge and lasso, but for ridge we have only one 0 coefficient, and actually this is just because we generated the original function in that way that we do not need this constant term. Just the only reason why we have it equal to 0 in all models, so we can just ignore it. As for the remaining 8 coefficients, 8 because we have 8 polynomials, degree of polynomials equal to 8, we can see that in lasso this regularization removed almost all unnecessary polynomials. So we know that we need just 4. 1, 2, 3, 4, 5, 0, 6, 0, and 8, 0. And the only remaining polynomial, unnecessary polynomial, is equal to the 7th degree. Well, it's not ideal, but here within this two example, it allows us to remove some definitely unnecessary terms from the final model. So this is the core difference between ridge and lasso. And if you work with a huge set of features and want to create a simple model, say you have 200 of features and you want to create a simple linear combination of 10 features to show this model to your, say, colleagues from an applied field, from biology, from industry, whatever. And sometimes it can be useful to create a small compact formula with 10 features instead of several hundreds of the original features. Okay, this is the last topic for today.